Okay, if you guys still remember the last experiment that we did, we pour solution A and solution B together, and we waited for a few seconds, then the whole solution changed color, right? So I haven't had time to finish grading all of your sheets, but today I would like to first start talking a little bit about that experiment. Okay, so that experiment is related to the experiment that we're going to be doing today. So last time, that's what's called iodine clock reaction, right? So initially we mix two solutions together, it doesn't change color. That is because despite hydrogen peroxide is known to oxidize iodide back to iodine. Okay, but however, we have a reducing agent that is present in one of the solution, right? And this reducing agent is actually called sodium thiosulfate. So this is not a very common sulfate that you would see in a normal textbook, but I think it's worth mentioning. So thiosulfate look like this. So it had two sodium ion next to it. So what it can do is a very common indicator used for titrating for iodine, because iodine is capable of oxidizing this sodium sulfate into its dimer, okay? So the electron move around, then you will end up getting this tetrasulfur salt, okay? The reason why you do not see the appearance of iodine is because the reducing agent is converting iodine back to iodide, okay? And once this reagent is consumed, then you see the solution become dark purple, right? And you also see some floating solid, which is likely to be iodine. So what's so special about this reagent, sodium thiosulfate? Okay, so anybody have a fish tank at home? Nobody? Okay, well, so normally we know the tap water contains chlorine, right? So you can buy these special, what is called the water conditioner from the pet store. So this is a chemical that you put a few drops into the tap water, then you can use it for your aquatic life, right? So because we know chlorine, the dissolved chlorine, they do some sort of reaction with water. These are oxidizing species. And then there could be dangerous to the aquatic life. But however, when you're adding sodium thiosulfate, that is under slightly basic condition. It can react with sodium hypochlorite acid. And under slightly basic condition, it will completely consume this hypochlorite acid back to sodium chloride and sodium sulfate. And of course, this is a redox reaction. You see that? There are some chemical species, their oxidation state change. And it generates water. And I'll come back to this at the end of this lecture because we'll be talking about how to balance a redox reaction involving metal, okay? This chemical can convert your hypochlorites into non-toxic salt, okay? These are going to be dissociated, completely dissociated. If you remember from previous chapter, group 1 cation, they're generally fairly soluble, okay? So, and a lot of you on the response paper, I see you recognize the buffer, okay? So before we talking about buffer, I want to remind you guys, okay, buffer can avoid the sudden change of pH. Why do we want to add a buffer solution to the system? This is because under acidic condition, sodium thiosulfate will degrade, okay? It will react with acid and form a very toxic gas and sulfur. So this is what's beautiful about these sulfur compounds. They can undergo so many different kind of reactions. So I know all of you know how to assign oxidation state at this point, right? You can identify what is an oxidant, what is a reducing agent, and all that, because these concepts are important for the chapter 21. And I'm impressed a lot of you recognize the bubble might come from the iodide catalyte decomposition of hydrogen peroxide. So that is also a competing reaction. All right, so now I will begin the demonstration for today. This is a multiple equilibrium. So I have 3 solutions. I mean, of course, the first one is being hydrogen peroxide, and also mix up solution B and C, and I'll email you guys the ingredient in it, and then you guys can start testing, coming up with some idea or some hypothesis. All right, so the first one, I'm gonna mix equal amount of them together, but I would like to be able to stir. So okay. Okay, so can you guys see it? Okay. Okay, so you guys have some clue. I mean, there are some iodide in it. Okay, so usually we think reaction is a one-way street, right? For a spontaneous reaction, which we'll be discussing, the Gibbs free energy, once it reaches a chemical equilibrium, it stops, right? Unless you change the reaction condition. And look, I'm not changing anything here, right? I simply mix 3 things together. So why? It's able to change color back and forth, okay? And then to confirm that what the color changes is the iodine starch complex, I'm going to add a little bit more starch in it. Because there are multiple kind of reagent in it, so you have multiple equilibrium going on, right? Okay, so I'll give you guys a few minutes, write it down, and I will set up the second one that do not have any stirring, okay? So this one is without any stir bar. So I'm going to carefully putting my third solution in it. Okay, it may not be so obvious, but you guys can come up and look at it. I mean, it's because it's not being fully mixed, it's not so obvious. So what I want you guys to look at is the layered effect. Okay, depending on the layer I put in the solutions, they separate out, and it is limited. This reaction process is also limited by diffusion. Okay, so if you think about what is perfect mixing, 是一种有机酸跟一种金属催化剂。All right, so I'm going to mix the first one again so you guys can observe, okay? You can see there's a difference in color, right? But because I'm not mixing it, it doesn't change as fast, okay? Okay, I'm going to put a little bit more indicator so we can see the color better. So it depending on the concentration, right? The color, the appearance of the solution will be different. Why? Why is that? Okay. And you can also try to observe the difference in time between each stage. Okay, is it getting faster or getting slower? Okay, then you will observe the formation of gaseous species, right? They're likely to be oxygen coming from the decomposition of hydrogen peroxide. So why it doesn't happen first? Okay, think about these, okay? So now this is with mixing, but the ratio is different. So you can see there's some purple compound floating on top. I'm not sure if you can see it from here. So it's really depending on the amount of reagent that you have in the system, all right? I'll give you guys 5 minutes to work on your study sheet, and we'll start talking about electrochemistry. So now you can see there's some purple solid form, right? Okay, so I'll get started for today's lecture. So for this week's target is we'll finish chapter 21 and accept 21.4 because that needs some thermodynamics before we can talk about it. Okay, and we'll also skip the calculation for the electrolytic cell. Okay, so on Friday, I'll be talking about some battery stuff. So today is just quickly go through electrochemistry. Okay, so electrochemistry is a subfield that is still remain popular. So we have known how to use battery for many years, but a lot of faculty, a lot of professors in Taiwan, their research program are still on electrochemistry. They care about the redox state of different inorganic species, organic species, all right? And why do we care about electrochemistry so much? It's because chemistry is all about electrons, right? It's about how electrons interacting with each other. So if you can eject an electron and accept another electron, some magical things happen. Okay, so for electrochemistry, for one instance, you will think of electrolytic cell. Okay, that means you use electricity to drive chemical reactions. So a very classic example is electrolysis of water, which will give you hydrogen and oxygen, right? So in high school, you guys probably seen this so many times. And also there is electrolysis of a brine solution, a very high concentration of sodium chloride solution, and then it will generating sodium and chlorine, and of course the sodium will immediately react with water and form sodium hydroxide. So this is electrolytic cell. The big difference between Voltaic cell, what you've seen here, a Voltaic cell is this is a spontaneous process, which means it will happen on its own. So it's giving out energy because when the electron travels through this wire, it can do work. It has a certain amount of energy in it. For electrolytic cell, it's about using electricity to drive chemical reactions. Okay, so once we get hydrogen, we can burn it and harvest its chemical energy. It's all about energy. So there's a tremendous amount of effort in understanding how can we generate hydrogen with minimal cost. Once we generated hydrogen, a lot of people are figuring out how to store the hydrogen, right? And how to use it safely. So now there's already hydrogen fuel cell car running around on the street. Not in Taiwan, but in the US, in Germany, it's feasible. But if you were to tell someone, hey, I'm gonna drive a hydrogen fueled car, 10 years ago, people might think you're crazy, right? Because the technology hasn't catch up yet. We weren't able to manipulate hydrogen safely. Okay, so there's a lot of electrochemistry in such old chemistry, right? And then there are so many efforts in designing new catalysts to make this more efficient. The next molecule I want you guys to think about is carbon dioxide. We know we generate carbon dioxide by burning fossil fuels. With the increasing human activity and production in the manufacturing sector, we generate a lot of CO2, right? So a lot of people in academia are working on developing catalysts or system that can reduce CO2 with electricity. So putting some electricity into CO2, and they want to convert that into CO and other useful chemical compound, okay? But the activation energy for such process is usually high, and it's consume a lot of energy. How can we make it more feasible? You have to understand electrochemistry. Understand what's happening at the interface, okay? It's all about interface. So let's think about a Voltaic cell, okay? Why the electro interface is so important? On the surface, if you take a very precise transmission electron microscope, you can see the atom, okay? So imagine you have a layer, a copper atom, perfect layer. Let's not worry about the oxide that's present on the surface. A perfect layer of copper atom, okay? So it was slowly, the solution, copper 2 from the solution, once it becomes solid, it was slowly depositing on the surface of these electrodes, okay? How does that change the diffusion process? I mean, this is why we did this reaction to have you guys start thinking about diffusion, okay? How can the different chemical species meet each other and mix so that reaction can happen, all right? So for a basic Voltaic cell, you will see a setup like this, okay? And then in the middle, that's called a salt bridge. And I know you've seen it on the paper, salt bridge, but really it's just a tube that connect two cells together and with or without a membrane in between. But for more advanced battery, a lot of people work on this ion selective membrane. Okay, so you only let certain type of ion pass through because we can think about, when we think about ion, it's made of different atoms, right? Some ion is bigger, some is smaller, right? So we can use size to select for the ion that we want, okay? All right, so when we put a solution like this, zinc is dissolving away, and the copper 2 is being deposited on it. So this is a spontaneous process, okay? So it releases energy, okay? So generally you can think of when the process releasing energy is spontaneous. I know this is in the thermodynamics part, but it's really hard to not to mention that, okay? Okay, so you guys already recognize the redox process. I just want to refresh. Wherever oxidation happens, that's the anode, okay? And the anode will give the electron off, and then the electron will transfer to cathode. A good way, I mentioned it last Friday, but I know some of you weren't here. The way I memorize it is, I know A comes before C, and then we said 氧化还原反应, so oxidation is before reduction, even though in English, you say redox reaction, it's reduction and oxidation, right? So, but if you remember the oxidation reduction, you can simply, you don't really have to memorize oxidation and anode and or reduction with the cathode, right? Okay. You simply just write it down, A and C, and you know A to the C, right? That means electron flow from anode to cathode, okay? So you just remember these pieces of information and you can piece this together. It's about how you use this knowledge to solve problems, okay? So zinc will give off electron, and the copper 2 will happy to take those electrons and become the solid, okay? What's the role of salt bridge? Okay, so one important thing in electrochemistry is a balance of charges. And we also recognize that pure water does not conduct electron, right? It's not conductive. So you will need some salt in the solution, right? So generally, in the salt bridge, I mean, you will see people have these notation. The sulfate will go to the anode, okay? The anion usually go to the anode, cation go to the cathode, okay? Because they want to compensate for the loss of copper ion, okay? And of course, the real picture is much more complicated if you can recall effective concentration, all right? So electrochemistry is a very complex process, all right? So in reality, people won't use a metal bar as the electrode, okay? So a lot of time people will use something we call inactive electrode that is decorated with the active compound, okay? So think about catalysts. For inactive electrodes, so we know graphite have excellent conductivity, okay? So graphite is one of the popular choice. Or sometimes you will hear carbon electrode that's made of graphite, okay? And platinum is also commonly used. All right, so let's go back to the basics. We'll start talking about balancing equations before we move on to potential energy, okay? So I'll take this old example up here. It's in your book, and then there's a lot of rules, right? And then it might be hard to understand, but I would like to walk you guys through how would you balance the equation. And I know you guys probably have other ways to do it. It doesn't matter as long as you can get the right balanced equation. So let's look at this example. When I know I have a redox reaction, I have an oxidant that is reducing agent that reduced my iodide back to iodine. Okay, so first I will balance this equation, right? So 2 iodide give off 1 iodine. So we need to account for the electrons, right? So we know this is -1, go to 0, okay? So with the 2 here, that means we have -2 up here. So we need to use 2 electrons to balance off this equation. All right, so the important thing about dealing with redox reaction is to know which species are being oxidized, which one are being reduced. Okay, so if you mess up your calculation, that's a very serious mistake, all right? And then for the reduction side, we generally add electron to it. And for oxidation side, for reduction, we normally add electron on the other side. And for oxidation, we'll do it, put the electron on this left side to balance the equation, okay? So let's consider another case, a more complex case. We use iodide to react with dichromate. And in your book, you probably will see they have the notation here to tell you what's the state of each component. But for simplicity, I tend to leave these off, okay? But why does it matter? Okay, if we go back to the calculation of reaction product, right, the Q, right, then it matters because we're talking about reaction system. Electrochemistry, electrochemical reaction is also a type of reaction. Okay, so let's consider this. We know oxygen normally it will stay as -2, right? So in order for this, so we know that here's -14, so chromium must be +6. That makes sense? Okay? And here, the problem already tell you, you form a chromium 3. So let's balance the dichromate, okay? This is another rule. First, we balance the atom other than O and H, and then we work on O, oxygen, then finally we'll work on hydrogen. When you have excess of these, you will use either water to balance off these extra atoms, okay? So if we look at this dichromate species, so first we recognize there are 2 here, right? So we will put 2 over here. But what happened, like I said, what happened to the oxygen here? It generates water. And you've probably already seen it if you think about the iodide catalyzed decomposition of hydrogen peroxide. You generate water, right? And again, there are 7 oxygen, okay? That's why I put a 7 here. Okay, so now if we look at this equation, I have excess amount of hydrogen here, right? So to balance this equation, you can either put hydronium ion in it, okay, or simply put H+. But H+ is not a real thing because we're dealing redox reaction in solution. It's actually present at H3O, but it doesn't really change the story, okay? Because H+ plus H2O is H3O+. Okay, so now because there's 7 water molecule, so that come out to be 14 hydrogen. Now we have to balance for a charge. So this is +14, -2, right? That's +6 and 0, okay? So this come out to be 12. So that means that is 6 electrons short. Okay, so how can we reduce the excessive charge here? So electron, recognizing electron carrying a negative charge, right? So we'll put electron over here. So then this come out to be a balanced equation. That makes sense? Okay. So recognizing on this side, on this iodide to iodine part, you only have 2 electrons in this process. But to complete this reaction, you have to use 6 electrons. This reaction might multiply the integer by 3. Okay, so that will become 6 iodide That makes sense? This is simply balanced equation. Okay, now these 2 reactions are balanced, okay? So because we only focus on one species at a time. Of course, you can look at this equation and start doing your magical math manipulation, and you can get the same result, but it's really easy to make a mistake. So in the end, after you make sure this number of electrons are the same, then you can add these 2 equations together. Okay, so there shouldn't be any electron left off for a balanced equation. All right, so if you don't remember, read your book, and there are some information in there. Let's do another problem. So for those of you who are chemistry major, you're running into this again in organic chemistry, okay? Balancing redox reaction. So in organic chemistry, we care about element other than carbon. But of course, there's a lot of organic chemistry involving inorganic chemistry because you need to make the ligands that enable your metal center to undergo these complex redox reaction. Let's look at a simple case. Don't be scared when there's a lot of charges, okay? So first, what we will do is to assign oxidation state for these compounds, right? So this will be +7. And we know oxygen is always -2 unless specifically mentioned. So carbon will have a +3, +4, +4. Okay, you guys will know because which one is the reducing agent, which one is the oxidizing agent, right? So let's write the half cell reaction. So let's focus on C2O4. Already balanced, but then there is 4 oxygen, but on the other side there's 6 oxygen, right? So we will use water molecule to balance such a reaction, right? So I give it 2 H2O, and then I will do the same thing here, use H+ to balance that extra oxygen coming from here, okay? Then I will check whether the charge is balanced. Okay, here's -2, but here's -4, +4, okay? So I need to be -2, so I add 2 electrons here. And same for MnO4, the permanganate. What you can do, if you work out your thing, you will get this expression. Okay, then you can check, then you simply do what I mentioned before, right? You balance the amount of electron in your sub-reaction, then you can actually balance your initial redox reaction. That makes sense? All right, so one thing I forgot to mention is for notation of voltaic cell. The idea of notation is so that people can understand what your system look like. Okay, so typically when you draw a diagram, the anode will be on the left, cathode will be on the right. This is a general rule, but you can't always assume so, all right? To use a simple, this is a language of electrochemists use to show my device structure. So this is called a device or my reaction setup. They will write, on the far left and far right will be your electrode material. And then it will have one line here separated and then say what's in solution. And then when you get to the other side where the oxidation happened, where reduction happened, you use this double line to separate them. Okay, and again you will put in the aqueous, the stuff that dissolved, and then it will have the state. So you know, okay, these are the part of your ions that are present in your solution, make it conductive. And then we'll put the line here. This is like the chemical equation for electrochemists. They show their device setup. Okay, sometimes they can put concentration here because for these things to work, these are off equilibrium system. And speaking of equilibrium, you guys can look at chapter 21.6. So it talks about the environmental application of voltaic cell. And we know corrosion, the corrosion process is about oxidation of iron to rust, right? So rust is the oxide of iron, different kind of iron species. So there's a redox reaction. So in fact, how can we stop this process? We can put some inhibitor that will react with, capture these electrons, or we can use the sacrificial magnesium rod, okay? So you put in a more active metal to undergo these redox reactions. So it will protect your iron, protect your metal. Okay, now we will talk about a little bit about electrical potential, which is the 21.3. Okay, how do we quantify such process? So one important, identify what's your cathode and what's your anode. There is a value called standard cell potential. Okay. When it says standard, that's 25 degrees Celsius, okay? these values can be measured, all right? So when we see E cell, it's talking about a complete circuit. And then the general way to calculate such value is taking your value from cathode minus anode. All right, so you can get a voltage, and you can look up this value by looking at table 21.2, which is on page 954. So as you can see from this table, when you are below hydrogen, that is a reference, we set that to 0, okay? So everything, when you see these standard cell potential value, is all relative to hydrogen, okay? And as you can see, for the metal that generally spontaneously react with water, it has a very negative value. And then in high school, we talk about the activity of metal. Some metal is more active than the other. This can be explained by this half reaction, the electrode potential. All right, so I want you guys to discuss with your partner to see what kind of pattern can you observe by connecting to the knowledge point that learned from the high school, why some metal is more reactive than the other. Think about zinc, think about magnesium, think about silver, right? You see any pattern from this table? Okay, so we know that zinc is more active than iron, right? And of course, zinc can displace copper ion, right? Undergo redox reaction, convert copper ion to copper solid, right? So if you look at the potential, it's near the bottom of this table. It has a negative half cell potential. So we can use this equation and calculate your value, right? When it's a positive value, when it's larger than 0, that means this reaction is more feasible, okay? The redox process will happen. And then when you look at this table, in your mind, you have to flip the side so that it can fit your redox reaction. A better example is on page 951, okay? So once you identify what happened to these chemical species, you can immediately figure out which one is anode, which one is cathode. Set up this equation, and you can figure out how feasible this reaction can be. Okay, and then another thing I want to mention is we know copper in strong nitric acid, it will generate NO, right? These brown gas. Why is that? That has to do with the standard electrode potential of these reactions. As you can see, copper is right above the blue font, okay? Copper is way below in comparison to the position of nitrate, okay? So we know nitric acid, once it dissociates, it will form hydronium ion and nitrate. So this confirms why copper can be oxidized by nitric acid and form NO. And also in this table, we can see fluorine, right? Fluorine is probably the strongest oxidizing agent because its value is very high. Okay, it's at 2.87. And we think about chlorine. I know in the previous chapter, it's kind of like you have to memorize, okay, when chlorine dissolves in water, what happened? You form hypochlorous acid. Why? I don't know, the book says so, but this table tells you why, right? It's actually undergoing a redox reaction with water. As you can see here, that's why once the chlorine dissolves in water, it can be in a chlorine form, but it also prefers to become other compound. Okay, because there's some exchange in the electrons. Then when these elements change oxidation state, they can form compounds. And another thing is, okay, why does these metal, the metal from the first two columns react violently with water? You can see the potential difference, right? Even they're both negative, but one is more negative than the other, you will get a positive number, right? So you may wonder, why is this important, right? Because this is in electrochemistry, we rely on these tables to understand the origin of the origin of electron flow. And then in your appendix, and near the end of your book, there's a more comprehensive list of all different metal or elements, okay? So let's look at sample problem 21.5, which is on page 956. I mean, this is really simple. It's once someone gave you a random table with these standard cell potential or half cell potential value, you can simply list, so I'll give you a few seconds to read through the problem, okay? This type of problem is very simple, right? So you put the most negative one on top, right? We know the one has a more negative number or a slightly smaller number is more likely to function as a reducing agent, right? So you have to be clear in terms of which species is being oxidized, which species is being reduced. Then you can rank the relative strength of each things. Okay, so that's why we focus on electro potential, or is also called the half cell, the standard reference half cell. Okay, and I know previously I mentioned we will talk about how pH meter work. There is a brief discussion in the book. Then I recognize because without thermodynamics, it's really hard to understand where the equation come from. So we will hold on to it. Okay, but basically if you flip to page 967, okay, it basically when you have a concentration difference, okay, it will create a potential. And with that potential, the voltage of your cell, this is how pH meter work. Okay, we already did some work to calibrate your electrodes. So it basically is to figure out what's my voltage correspond to the pH, okay? When you basically apply, usually the platinum is used as an electrode and you have a concentrated solution as your reference electrode. And then this special membrane at the tip of your pH meter allow proton to go in and measure the difference in potential and you can figure out the pH value. So if your pH meter is not properly calibrated, that means your factor that convert pH to your electrical potential is different, okay, then you won't get the accurate pH value, right? And sometimes some people will put electrode into organic solution. Will you be able to measure the pH? Very unlikely, right? So whatever that value you get is more likely to be an instrument issue. Okay, and I think that's all I have for today.